Let's continue the mathematics of artificial intelligence by building a neural network from scratch. Okay, so the objectives here uh, include the following: that in this lesson, you will learn how to build a complete feed-forward neural network using only NumPy without relying on TensorFlow or PyTorch. By the end of the lesson, you will understand every mathematical operation involved in training a neural network, including parameter initialization, forward propagation, activation functions, loss computation, backpropagation, and gradient descent. Finally, you will apply everything learned to a handwritten digit recognition mini project. And of course, the prerequisites of this will be Python programming. If you don't already do Python programming, this may not be so easy. Then NumPy. NumPy is a special library in Python for numerical computations. Then you need to understand the mathematics of matrix multiplication, partial derivatives, chain rule, forward propagation, gradient descent, which is optimization. Then then of course we see the neural network architecture of 784 to 64 to 10, where 784 means you have input neurons 28 multiplied by 28 for image, and 64 which are hidden neurons, and then you have 10 which are output neurons for that is digits 0 to 9. This lesson builds every component from scratch. So let's go ahead and see this. First of all, you need to import required libraries. Unlike modern deep learning libraries, we only need NumPy for all computations because you are building from scratch, right? So to do that, you need to import NumPy as NP and import matplotlib.pyplot as PLT. Of course, NumPy is for numerical computation. So NumPy provides matrix multiplication, random number generation, vectorized computations, and efficient linear algebra. And throughout this lesson, every neural network computation will be implemented manually using NumPy. Then, of course, okay, we've seen, oh, NumPy provides all of this. Okay, I think I did that doubly. Let me delete one right now. Okay, I guess this has got to go. Yeah, yes. So, with that out of the way, then we move on to the data set recognition. So our mini project uses handwritten digit images. Each image has dimensions 28 by 28, and after flattening, we get 28 by 28, which is 784. So each training example therefore becomes, the inputs are in the 784. You have a 784 dimensional real number system, and possible output classes are number 0, 1, 2, 3, up to 9, and you have example normalization with something like X train. X train equals X train over 255.0, and X test is X test over 255.0. So normalizing improves convergence and numerical stability during training. So normalization, it's more like when you use things like log and all that to ensure that numbers are not wide apart, or even in data analysis where you get to standardized numbers and all that, so you can get more stable results. So let's talk about initializing weights and biases. Now, several times, right? We've learned about the fact that you have your inputs. It can come like a column vector X, and then you multiply that by weight and add biases and all of that. So talking about initializing biases, now weights should begin as random numbers. So we also had a video previously where we saw that weights and biases are random, but then the process of searching for the best answer is not a random one. So it's a guided search rather than a random search, so that you are actually going towards a particular result. So which should begin as small random numbers, like you have input size of 784, hidden size of 64, and output size of 10. So for weight one, that's the initial weight now. So you just take some random size. So you generate randomly input size, following this idea, and then hidden size also, and all of that multiplied by 0.01. That's the first weight there. For the first biases, you just generate zeros. So for the that go with the hidden size, and then W2 now, you do the same thing. So you have some randomness here, and then for the B2 now, you now have the output size. So this is what you start with, and this is what you end is with based on the system. So, okay, well, I mean, running this, I don't think it's that necessary, but let's see how that works. So the dimensions are W1, and the first weight is 784 by 64, as you can see here. And then the first bias is 64 dimensional real number. Okay, NP not defined here. Okay, I guess we should have, okay. So I think it's better to bring this one here and do it together. Although we still have a whole mini project after now. So this one's not the challenge is that NumPy was not defined here. So with this now, I think we shouldn't have that issue. Although this doesn't do anything because we're still going to do the mini project. So W2 is 64 by 10, and then B2 is a 10-dimensional one. So you see that linkage as you're going to go. So random initialization breaks symmetry. So neurons learn different features now. So and then you have the rectified linear unit activation. So the hidden layer uses the rectified linear units, right? Which is actually the default activation function used. So mathematically, ReLU Z is actually the maximum between 0 and Z. So we've seen that a couple of times. So here, ReLU avoids the vanishing gradient problem common in sigmoid networks and accelerates training. So that's why we get to use ReLU a lot like that. Then, so define the ReLU function, which is you just take the maximum of 0 and Z. And for derivative, you have ReLU derivative. So you return Z greater than 0 as type float. Then you then have to talk about the softmax output layer. So softmax converts raw scores into probabilities. I mean, in previous videos, there were videos earlier on that we talked about this a lot, how to compute the process. So given Zi, then the probability of class I then is EZI all over the summation over all the possible classes you have. So summation of all that is ZJ, and then you have the implementation shown here. So you have defined softmax Z equals Z minus NP max. So you have a subtraction of NP max here. So subtracting the largest value prevents overflow during exponentiation. We're still going to implement all of these things. So then you have the forward propagation now. Forward propagation computes prediction. So the hidden layer, for instance, you have Z1. So we learned before that forward propagation helps to get a prediction, while backward propagation helps to improve the prediction. That's now the process of learning. So Z1 is XW1 plus V1, and A1 now you apply the activation function to whatever you get as Z1. So if it's anything, if it is greater than 0, then Z1 will be the answer. If it is less than 0, if Z1 is negative, for instance, the A1 will be 0. So then you now have the output layer where Z2 is now given as A1. The A1 you got multiplied by the second weight plus the second bias. And then finally, you now have A2, which is computed as the softmax of whatever Z2 you get. And then you have the implementation here. So just an explanation because you're still going to do all of this later. So you have Z1, you take the ReLU Z2, and you bring the A1 here and A2, now you have softmax of Z2. So the matrix A2 contains the predicted probabilities for every digit. So this matrix now has the predicted probability. So in that way, you can then decide which digits comes out first. So look at the examples we can have here. So suppose X, the input is 1, 2, and then we have weight 0, 3, 0, 5, 0 0.3, 0 0.5, 0 0.4, 0 0.2, and then Z is XW. In this case, and then in that case, Z1 becomes 1 times 0 0.3 plus 2 times 2 times 0 0.4 equals 1.1. Say Z is 1.1, right? Like that. Okay, I mean, all of that is 1.1. That's Z. And then Z2, you have 1 times 0 0.5 plus 2 times 0 0.2, and you get 0 0.9 there. So Z is now 1.1, 0 0.9, like this. So you know it's XW, right? So you have 0, 3, 1, 2 over 0 0.3, 0 0.4, 1, 2 over 0 0.5, 0 0.2, 1, 2 over that, and you get Z to be 1.1, 0 0.9. So apply ReLU gives the same values because both are positive. So if I apply ReLU here, that's the rectified linear unit activation function. So you get 1.1, 0 0.9. So that's what you get in that case. So there we have not applied softmax, but let's go ahead and talk about cross-entropy loss function. Now, the goal of training is to minimize the prediction error. For multi-class classification problems such as handwritten digital recognition, the most widely used loss function is the cross-entropy loss because you have multiple classes. So for a single training example, the loss is L, which is minus sigma, summation from I equals 1 to C of yi log yi cap. So where C is the number of classes, then yi is the true label, which is one how to encode it, and yi cap is the predicted probability for class I. So we're going to have that for class I and so on for every class, like from 1 to C. So if you have 10 classes, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for a data set containing M training examples, the average loss becomes J equals minus 1 over M, summation over K equals 1 to M, and summation over I equals 1 to C of yi k log yi cap k. So, and then you have the NumPy implementation right here. So, and I mean, this is not a code, just explanation for now. We are going to implement all of this. So you define the cross entropy, you have the true value of y and the predicted value of y, and you have m now, which is y true shape 0 based on the number of training examples you have, and then you compute the loss based on the formula. But here you discover that instead of just having log y, we have log y pred plus 10 raised per minus 9, just a very tiny value like that. And then if you can then return the loss over m. So this small value is added to prevent taking the logarithm of 0. So if y pred is 0, for instance, so this small value will make sure that you don't end up getting taking log of 0, which is undefined, right? So the interpretation is that for perfect prediction implies very small loss, and incorrect prediction implies large loss. So training attempts to minimize this quantity. That is, training attempts to make the loss very small. Now, we then talk about computing cross-entropy loss. So suppose the network predicts y cap to be 0.10, 0.20, 0.70, and the true class is the third class, just this, right? So you see this one already predicts that the third class is 70% correct. So if we have that, so substituting into the cross entropy equation, we have L equals minus 0 log 0.10 plus 0 log 0.20 plus 1 log 0.70. And if you simplify all of that, of course, all of this will go. So you just have minus log 0.70. And using natural, of course, this is going to be negative. So it's going to cancel this out. So if you take all that, L is now approximately 0.3567. Now, if you consider a poorer prediction, so in this case, now the loss is pretty small. I mean, kind of small, maybe not so small, but at least it's small. It's less than 1. Now, consider a much poorer prediction, like you now have 0.60, 0.30, 0.10, whereas the correct one is the third class. So then you have L to be log 0.10 because you now have 1 log minus log 0.10. So that gives you a bigger loss, which is 2.3026. The observation here is that a correct prediction with high confidence produces a much smaller loss than an incorrect prediction. During training, gradient descent adjusts the weights so that the cross entropy loss continually decreases. So if you get this for starters, you keep recalibrating the weights and biases until you get a loss that is acceptable. Then we talk about backpropagation, which you had seen in a previous video. So in fact, I think the last video was totally dedicated to the idea of backpropagation. So backpropagation computes how every parameter contributed to the prediction error. So for a softmax output layer combined with cross entropy loss, an elegant simplification occurs. The derivative of the loss with respect to the output logits is dz2 equals a2 minus y, where a2 is the predicted probability matrix and y is the one-hot encoded target matrix. Now, using this result now, you can get dw2, which is 1 over m, a1 transpose dz2, then db2 is, that's for the weight now, and for the bias, you have 1 over m summation dz2. So when you take the derivative, so for backpropagation, you're taking the gradients of all of the weights and biases with respect to each parameter. So the NumPy implementation is something like this. You have M to define the number of classes you may have, and dz2 is a2 minus y. So the w2 is now a1 transpose, a1 dot c, which is a1 transpose, then multiplied by dz2 divided by the number of classes, and then db2 is the sum of dz2, the derivatives of z2, and then, as the 0, you keep dimensions to be true and divide by m. And then in this case, the dimensions are dz2, you have m by 10, dw2, you have 64 by 10, and db2, you have 1 by 10 at the end of the day. So these gradients tell us how every output weight and bias should be adjusted to reduce the loss, like this. Then we go on to talk about backpropagation through the hidden layer now. So the error at the output layer must now be propagated backward, and that's why it's called backpropagation. So the error at the output, so once you make a prediction and you get a result, so you have to check the loss, right? And whatever the loss is, you now do a backpropagation. So the error at the output layer must now be propagated backward into the hidden layer using the chain rule. So first you have DA12, which is the Z2W2 transpose. Since the hidden layer uses the ReLU activation, so DZ1 is DA1 multiplied by ReLU ReLU prime of Z1, where this dot now, this notation is actually, it denotes element-wise multiplication. And finally, you get the W1 equals 1 over M X transpose DZ1, and DB1 is 1 over M summation DZ1, like that. And then you have the NumPy implementation also described here. So you're going to implement all of this at the end of the day. So you have DA1 to, which is DZ2 at W2 dot transpose, and then you have this one. So pretty much everything you have here are put in equation form right here. Okay, so in dimensions, now you have DW1 to be 784 by 64, and DB1 ends up being 1 by 64. So at this stage, gradients have been computed for every trainable parameter in the network. And the next step is to use this gradient using these gradients to update the parameters using gradient descent. Then we have 27.10. So updating the parameters with gradient descent. After computing the gradients through backpropagation, we update every weight and bias in the direction that reduces the loss. So the general gradient descent update rule is theta new equals theta old minus alpha dj d theta. So I mean, we've dealt with this a whole lot. In that case, we call this dw d theta or something like that. That's actually the LDW exactly. That's the gradient of the loss with respect to each parameter. So where theta represents any trainable parameter, and alpha is the learning rate, and j is the loss function. In fact, I think we had made separate videos talking about things like learning rate. Like when you have two big learning rates, you have you have a kind of oscillation happening instead of having converging towards a particular solution. So for a neural network, we have W1. W1 is then back. So you have W1 minus alpha DW1 going back to W1, and then B1 minus alpha DB1 going back to B1, and you have that for W2 and B2 also. So for the NumPy implementation now, you have so you talk about the learning rate 0.01 and W1, you know, this is being reduced, right? So W1 is actually minus equals. That means that whatever you get here, you subtract again, you go back and you get a new W1. So this minus equals means that the weight and B1 will keep being adjusted until you get what it should get. So why does this work? The gradient points in the direction of the greatest increase in the loss. All right, so the gradient points in the direction of the greatest increase in the loss. So subtracting the gradient moves the parameters in the direction of the greatest decrease in the loss. Repeating this process thousands of times gradually improves the model's prediction. So at the end of the day, we are moving closer and closer to a J that is as close to zero as possible, because we want no loss at all. We want no error as much as possible. Then we have the complete training loop now. So training a neural network simply repeats four steps. You have forward propagation, which makes the prediction. And then after the prediction is made, the loss is computed. And then based on the loss now, we have a back propagation. So we take a derivative of the loss function with respect to every trainable parameter. And then based on that, we see how each parameter contributes to the loss. And then based on that, we make a decision on how the parameters will be updated to get closer to a loss that is acceptable. So this repetition is performed over many epochs, and then you have the NumPy implementation here, which is also still just an explanation. Imagine you have 100 epochs. So for epoch and range epochs, you have forward propagation. Z1 is this, A1 is that. Of this we've talked about before. Z2 is this, A2 is this, and then you have the loss, which takes the cross-entropy of Y and A2. Then you have the back propagation, which takes derivatives like that. So if I run this now, let's see. Okay, I mean, this is not meant to be run. It's just for explanation because they're still going to run it at the end of after now. So the expected behavior here, as training progresses, the loss should decrease. That is so this is a combination of everything we've been talking about before we got here. So let me see if I can fit that into one screen. Okay, I think it's a lot. Let me see. Can it still fit in? Okay, I think it's better to just leave it the way it is. So I'll just flash it a little bit. So you have for 100 epochs, you define the forward propagation. Then you define the loss, the back propagation, like this. So, okay. So you have the loss and back loss, forward propagation and loss here, right? Forward propagation determines the loss for sure. And then once the loss is determined, you now talk about the back propagation, which is derivatives, differentiating the loss with respect to every trainable parameter to see how they contribute to the loss. And then once that is done, we go on to the gradient descent, which helps to reduce, to adjust the weights and biases so that we can move closer and closer to the required loss, to an acceptable loss, right? So the expected behavior is that as training progresses, the loss should decrease, prediction accuracy should increase, the network gradually learns useful image features. So making predictions now. So after training, the output layer produces a probability distribution over the 10-digit classes. So here, we are doing this neural network from scratch for digit recognition. So the predicted class is simply the one with the highest probability. Mathematically, Y cap is the maximum argument of A2, across the possible classes. So where A2I is the predicted probability of class I. So if you have A21, and that's the predicted probability of class 1, A21, right? A22, that's the predicted probability of class 2, and so on and so forth. So you then have the NumPy implementation, right? So you have predictions, you have NP add max of A towards this one. So for example, suppose the network predicts 0.01, 0.03, and all of that, up to 0.01 again. The largest probability is 0.85, which you see here. So, and that is located at index 3. That's you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means 3 is the biggest located at index 3. Therefore, Y cap will predict 3 for you. So the network predicts that the image is the handwritten digit 3, like that. So imagine in that case, now once that is done, then you have to evaluate the model accuracy. So accuracy measures the proportion of correctly classified images. So the accuracy formula is this: number of correct predictions over total number of predictions multiplied by 100%. So suppose correct predictions made are 947 out of total 1,000 images. Then we can say the accuracy is 947 over 1,000 times 100, which is 94.7%. And then you have the NumPy implementation also. So you have the labels, np.argmax y axis 1. Accuracy, that's the average of prediction labels, and then the accuracy is printed. So the interpretation of this is simple, that accuracy equals 1 means every image was classified correctly. Accuracy 0.95 means 95% of images are classified correctly. Higher accuracy generally indicates a better trained model, although additional metrics such as precision, recall, and confusion matrices are also useful for more detailed evaluation. So we have all of this coming up in machine learning all the time. So finally, we are at our mini project. So the mini project, like we said, is the handwritten digit recognition, right? In this project, we combine all the components developed throughout this lesson to build a complete neural network capable of recognizing handwritten digits. So, problem statement: given an image of handwritten digits 28 by 28, predict whether it represents one of the digits 0, 1, 2, 3 up to 9. And then the project workflow will go this way. You load the data set. So, and then you normalize the pixel values. Then you want hot encode the labels. You initialize the network parameters, you perform forward propagation, you compute the cross-entropy loss, you perform back propagation, update the parameters using gradient descent, repeat for multiple epochs, and evaluate the trained model like that. So you keep evaluating until you get what exactly you get a result that is acceptable given the loss it gives. So the labels must be converted into vectors. For example, 5 has to be something like 0, 0, 0, 0, 0, 1, 0, 0. So that means, so when you are dealing with 5 now, so the one head encoding will put 1 in the place of 5. That's 0, 1, 2, 3, 4, 5, like that. So the NumPy implementation is this: you have define one hot y number of classes equals 10. So return np.I number of class that particular y now. So for 5, you have 5 here. So 1 will be put there. Now for data processing, you can have the X train equals X train dot as type float 32 over 255 X test also. The Y train is that 1/4 of the Y train. So after preprocessing, the neural network is ready for training. So now let's see testing the trained neural network now. Once training is complete, the model should be evaluated using images that were not used during training. So this provides an unbiased estimate of how well the network generalizes to unseen data. So you can then forward pass on the test set. So you have Z1, that's X test at multiplied by the weight plus bias, and then you have the ReLU activation function used on Z1, and you have Z2, and you test the predictions, and then you compute the test accuracy at the end of the day. Let's say that gives an example output of 96.48% of the handwritten digits in the test data set. So a high test accuracy indicates that the network has learned meaningful patterns rather than simply memorizing the training data like that. So how can we improve this neural network? So although the network built in this lesson is relatively simple, there are many ways to improve its performance. So better weight initialization. So instead of small random values, you can use HE initialization for ReLU networks. Say W is follows is normally distributed with mean zero and devi variation, right? Standard deviation 2 over NIN, which helps maintain stable activations. Then you have mini batch gradient descent to also improve that. So instead of processing the entire data set at once, divide the data into small batches. Say typically you have 32, 64, 128, 256 samples. Mini batches often train faster and improve generalization. Then you have advanced optimizers like so you can replace ordinary gradient descent with momentum, RMS prop, and Adam. We've seen that in previous videos. These optimizers convert more quickly and are less sensitive to the learning rate. Then you have regularization also. So you can reduce overfitting using dropouts, L2 regularization, early stopping, data augmentation. And you have deeper architectures. Instead of 784 to 64 to 10, you can consider 784 to 256 to 128 to 64 to 10. So modern deep learning models often contain dozens or even hundreds of layers like that. So that you want to get a correct answer as much as possible. So now complete neural network implementation is what we now have here. So this section brings together all the pieces to create a fully functional neural network for handwritten digital recognition. So we'll load so there's a popular dataset called the MNIST dataset. I think I used it a bit on under the machine learning playlist, and of course uh the basic Python basics also. We got to use the MNIST dataset. So we preprocess it, define activation and loss functions, initialize parameters, train the network using forward and backward propagation, and finally evaluate its accuracy. So see what happens there. Let me try to see if I can just so here we import necessary libraries like NumPy. We are building from scratch, so no PyTorch. Oh, we have TensorFlow still coming in here. So import TensorFlow for Keras. So this is for Keras dataset fallback here now. Then you have SK model selection, train test split. That's where we take some part of the data for training, and then we take another part for testing. So sklearn dataset. So here we fetch the OpenML dataset here. Then so for number one, you load the MNIST dataset. So you can print loading MNIST datasets. So we try loading with sklearn datasets dot fetch dot openml. So this is what is helping us to get the dataset. Then we have MNIST fetch openml MNIST 784 version 1 parser auto. Then you have x comma y, so you have the MNIST data and MNIST target, right? So X is the data you're putting in, and this is the target, what you want to predict. So convert to NumPy arrays and appropriate types. So yeah, okay. While I explain, let it start running because I think it may take a bit of time. So while I explain, let it just start running first. So convert to NumPy arrays and appropriate type. So you have x equals x to NumPy as type float. So you're converting to float type. Then y same is happening, and then you print MNIST dataset loaded successfully using fetch OpenML if it is successfully loaded. So that's a trial, right? If that doesn't happen, so you have an exception. So accept exception as so print one in fetch OpenML failed, falling back to Keras dataset MNIST. So we don't want to use Keras at all. Keras came with TensorFlow. We don't want to use that at all. But if this one fails, then we can fall back on this. So either way, we have our data set. So fall back to Keras data set if fetch MLO fails. So you then have X train full, Y train full, X test full, Y test full, and that is coming from Keras. That's if this first part doesn't work. And then you can combine train and test data to mimic the original XY structure. So you have X np.v stack this, Y np.concatenate, Y train full, Y test full, and then you can reshape and convert to float 32. So you have X is X reshape minus 1, 28 by 28 as type, float 32. Then, all of that. You then have MNIST dataset loaded successfully using Keras. That is if fetch OpenML doesn't work. So in this case, now you can split data into training and testing sets. So you have all of this. So you can then print loading MNIST dataset. That's from the beginning. So MNIST dataset loaded successfully using fetch OpenML. Training data shape, you have 56,000 by 784. Training label shapes, you have 56,000. Test data shape, you have 14,000 by 784. And test label shapes, you have 14,000 like that. And then you can have helper functions now, like the activation function. So ReLU activation function and its derivative. So you define ReLU Z, that returns the maximum, and you take its derivative. So that returns Z greater than 0 as type float here. So, and then you have the softmax activation function. So you define softmax, which subtract maximum for numerical stability. So z now is z minus the maximum value of z you ever have, and then you take the exponent of the z and you return exponents over sum of the exponents, which we know it gives us the softmax. And then you have the cross entropy loss function. So you define the cross entropy y through y pred. M is the number, the shape y through the shape 0. Add a small epsilon to prevent log, so log 0. So in case y pred is 0 now, we have an undefined function. But if you add this 10 raised to minus 9, you prevent that on infinity, and then you turn loss over m. So you have one head of encoding function. So I run all of that also. So, and then we have the data processing part here. So for the data processing, you normalize pixel values to be between 0 and 1. So you have x train underscore num equals x train over 2.255.0. You know, we have the 256 thing going on there. Then x test num, you have x test over 255. Then one hot encode training and test label. So you have one y train, one hot. That's one hot y train. Then y test, one hot y test. Used for loss calculation during evaluation. Then you can then print data preprocessing complete. So don't forget to run this. Okay, so with all of that in place, then we can move on to, okay, we've done activation function, we've done data preprocessing. Then we have network initialization and training. So neural network architecture parameters for the input size, you have 784, hidden size, you have 64, output size is 10 because we are talking about digit 0 to 9. Then you can initialize weights and biases. So we initialize it for a fresh run. So np.random seed for reproducibility, if not because we have a lot of randomness, this line helps us to make sure that we keep getting the same results instead of getting different. If we remove this line 7, you keep getting different results, and that can be frustrating, right? So that's why we put that seeding for reproducibility. So you have the with W1, W2, and with W1, W2 and biases B1 and B2 defined like we saw before. Then we have the hyperparameters. Okay, I think I should even get this running in case it's going to take too much time. Then you have the learning rate to be 0.1. This can be increased for learning rates for faster convergence. And here we have 500 epochs, so that's going to take a bit of time. So I'm probably going to take the practice problems and come back and still have it running, possibly. So, but I've started running it already. So sprint, you can start training for epochs with learning rates, whatever the learning rate is. So you pick all of this now. So for instance, start training for 500 epochs with learning rate 0.1 like this. So you then have the training loop. So this is where the work now goes on. So from step by step. So for epoch in range epochs, so you have four propagation. Z1 is X train underscore norm at W1 plus B1. A1 is really 2 Z of Z1. So same thing we've had before, except that now we are doing the actual thing, you know. So you see the epoch has started. So starting training for 500 epochs with learning rate 0.1. So far we have just we are still on the we are still on the first epoch, so to speak. So from 0, so it is done in 50 epochs, in 50 jumps, as you can have here. So if epoch divided by 50 is 0, or epochs is -1, so print epoch. So we are doing it in 50s like this. So you can see the loss is getting better. It started from 2.3027, now it is 2.10. So it is going to go in 50s until we get to 500. So we'll come back to that later. Okay. Well, from what we did previously, I'm still going to run all of this, but from what we did previously, so for the model evaluation gives us a test accuracy of 0.90 to 1. So example predictions now. So this one predicted 8 and it is actually 8. This one predicted 4 and it is actually 4. This one predicted 5, but it is 8. So that's an error there. So we can have some errors. So it calls this 5, but it is 8. So this one predicts 7 and it is 7, which is true. So we have one error, right? This one predicted 7 and it is 7. This one predicted 0 and it is 0. This one predicted 6 and it is 6. This one predicted 2 and it is 2. This one predicted 7 and it is 7. This one predicted 9, but it is 4. So you have two errors now out of all of them. So at the end of the day, you have the predict the test accuracy to be like 90.21%, because out of maybe 11 predictions, we have 2 correct. So you can see the epochs are still going like that. So we'll probably come back to it later. So of course, these other ones had to follow that, but see, I did it so that because I know it's going to take a lot of time, and waiting can actually not be so useful. So here, the summary, I'm going to come back to the epochs later, right? So as you can see, just as I showed you now, you can see the loss is getting better and better for every epoch, for as the epochs are increasing. So 0 to 50, the loss moved from 2.30 to 2.10. From 50 to 100, it moved from 2.10 to 1.07, and it keeps going. So by the time we get to 500 epochs, the loss will be significantly close to 0. Okay, and these are the results you are going to get at the end of the day. So in summary, uh, I mean, I can congratulate you. You have successfully built a complete feed-forward neural network entirely from scratch using only NumPy. Normally, at advanced level, we get to use things like PyTorch and TensorFlow. So we have learned to implement parameter initialization, ReLU activation, which is the default activation function used in most of AI, except otherwise stated. And because we know things like sigmoid activation function has problems of vanishing gradients, so that's why ReLU can be a good one here. Then we have softmax activation, forward propagation, cross-entropy loss, back propagation, gradient descent parameter updates, prediction and model evaluation. I didn't talk about the model for the model evaluation. Okay, we talked about it here. We saw that the test accuracy is 0.90. So this is the code to show how well your model performs. This one is still running the epochs. Now it has 150, in fact 200. So it has gone to 0.5 all the way from 2.30 like that. So yeah, so we then have the complete mathematics pipeline. We've seen this a lot, So you have the forward propagation, which is Z1 is all this. We've seen this a lot. Then you have the loss computed, and then you have the backward propagation, which helps which is where the training actually happens. So, and you finally have the gradient descent, which helps us to get closer and closer to what is required. So this sequence of operations forms the foundation of virtually every modern deep learning framework, including TensorFlow, PyTorch, and JAX. So all the PyTorch and TensorFlow, which are really advanced, are based on this basic idea, and that's why we can actually use it's more like using first principle. Now, this video is all about the first principle of neural network building. So, understanding how these computations work from first principles provides the mathematical intuition needed to design, debug, optimize, and extend neural networks for real-world artificial intelligence applications. So at the end of the day, we have these practice problems, and I get to solve two of them. In this case, I'll be taking care of questions. Let me see now. Questions. I think it's two part of this. Let's check. So solve the following problems without using TensorFlow, because we are building from scratch, right? So without using TensorFlow or PyTorch, unless explicitly instructed, show all mathematical steps where appropriate, And here I'll be taking care of questions 5 and 17. So I'll be taking care of this question, which is this question 5. A CNN layer uses 64 filter. Is that question 5? Let me see. Then there's 17 also. Okay, looks like okay, 6. Yeah, so I'll be taking care of 6. Complete the softmax probabilities for the output vector z equals 310. Then after 6, we'll also deal with 16. 16 is estimate the total number of trainable parameters. Yeah, so 6 and 16 here, 6 and 16. So again, look at the problems. Yeah, you see 1 to 5 clearly here. And then, after that, so you can see 1 to 5 clearly here. Then you have 6 to 10 clearly. I'll be taking care of 6. Round your answers to 4 decimal places. I'll take care of 6. Then you can see 11 to 15 right here. And then I'll be taking care of question 16 here. So, and then we have all of that up to 20. So let's go ahead and take care of these ones. So 6 and 16. So let's start with 6. So still dealing with mathematics of AI. Can I squeeze this in? What can I do with this? to get it out of the way. Okay, let's just do what we have to do here. Trying to see if I can shrink this. Okay, no worries. So let's just go with this. So here now, we have problem 6. Problem 6. It says to compute the softmax probabilities for the output vector z equals 310. Round your answers to 4 decimal places. Yeah, I think we've done something like this in earlier videos. So which should I pick now? Okay, let me go for this. So solution, okay, maybe this is too big. So where is the eraser here? Yeah. Okay, so let me do this. Oh, maybe that's too small. Okay. Yes, it's too small. How about this? Okay, yeah, I think I'll just use it like that. Right. All right, so solution. So we know that the softmax function is defined. I feel this is too big actually. So let me see if I can reduce the size. Yeah, I think it should be better. The softmax. So better. So the softmax probabilities, or better still, the softmax function is defined as P sub I equals e raised power zi all over summation from j equals 1 to n of e raised power zj. So if that is the case, we can go in steps. So for step 1 now, step 1, we compute the exponential, of each component, Don't forget what we are working with. We are working with 310 this. So then that means that we have e raised power 3, that's 20.0855. We have e raised power 1, which is 2.7183. And then we have e raised power 0, which is 1.000, like that. So if that is the case, we move on to step 2. So in step 2 now, we compute the denominator by adding up all of these things. Compute the denominator. So that means we have 20.0855 plus 2.7183 plus 1.000, which is all equal to 23.8038. So with that done, then we move on to step 3. In step 3, we compute each probability. Compute each probability. So compute each probability. So for the first class, for the first class, we have the probability as P1, that's 20.0855 all over 23.8038, and that is equal to 0.8438. Okay, then we have for the second class P2, P2 is 2.7183 all over 23.8038, and that is equal to 0.1142. And then we have the third one. Don't forget all these results we got. So this now, each of them. Then we have for P3 now. So P3 is equal to 1 all over, if you like, 1.000 all over 23.8038, and that is approximately, or let's say, that is approximately 0.0420. So the final answer now, final answer is that the softmax of Z that we are given is 0.8438, 0.11, 0.1142, and 0.0420, all of that. So the interpretation of all of that is this now. So you can see, this corresponds to 3, this corresponds to 1, this corresponds to 0. That means that 3 gets the highest prediction probability. So it's most likely going to be picked. So we say that the neural network predicts the first class, that's class 3, because it has the highest probability. Like that. So it has the highest probability 0. It has the highest probability 0.8438. So it means that the digit 3 will be predicted. Okay, let's go for problem 16. So here now, let's go purple. Okay, so that's problem 16 now. Problem 16. So problem 16 says, okay, I guess I can do this. Problem 16 says to estimate the total number of trainable parameters. Total number of trainable parameters in a neural network. With architecture 784 to 128 to 64 to 10, like this. Include both weights and biases. Include both weights and biases. So this time, I guess we can use this. Yeah, okay, this is cool. So let's go. The solution. So the total number of trainable parameters, equals, that will equals the weights plus biases. So weights plus biases, that's important to take note of. So we have weights plus biases, and then we go step by step. Now in step one, we talk about parameters between the input layer, and the first hidden layer, and the first hidden layer. By now, we have normalized the idea that artificial neural networks at this level, the first thing you have is the input layer. Then at the last level is the output layer. Then everything in between can be said to be the hidden layer. So we already know that that's how this works. Okay, so you have two hidden layers. The output, the input, the hidden layers, and the output. So between parameters between the input layer and the first hidden layer. So the input layer is 784. The hidden layer you have 128, right? So let's see how that works. So in this case now, we have that okay, I'm still using this. So here we have parameters between the input layer and the first hidden layer. So here the weights are 784 by 128, which is equal to 100,000 and 100,352. Okay, 784 by 128. So you see this. So that's 100,352. And for the biases, right? So the biases, you have that to be 128. So the biases will automatically follow this idea of 128. So with that in place, then we have the total now to be equal to 100,352 plus 128. And that is equal to 100,000 and 100,480. So that's the total between the input layer and the first hidden layer. Now, let's talk about step 2. In step 2 now, we talk about parameters between the first and second hidden layers. So parameters between the first and second hidden layers. Okay, in that case, the weights here, so the weights, so as you can see from where we started from, right? So this is the first hidden layer and this is the second hidden layer. So we are talking about the parameters between all of that, between the first and second hidden layer. So automatically the weights now, the weights will have to be that 128 in the first layer and 64 in the second hidden layer. And if you multiply all of that, you get 8192. And automatically the biases will be 64. So here you have biases equals 64. And then that gives us total. So you have total to be 8192 plus 64, which is equal to 8,256. So that's gone. And then we move on to the next step. That's step 3. So in step 3 now, we talk about parameters between the second hidden layer, and the output layer, So then you have the weights. Again, we know the pattern now. You have the second hidden layer and the output. That's basically, so now we're talking about 64 and 10 here. So we know the weight will be 64 times 10 and the bias will be 10. So we already have seen that pattern. So the weight here, you have 64 times 10, which is equal to 640. And you have the biases. You have the biases to be 10. So biases, you have that as 10. So that total will be 640 plus 10, which is 650. So with all of that in place, we go to step 4, where we compute everything. So step 4, compute the overall total, and that is 100,480 plus 8,256 plus 650, and everything goes to 109,386. So that's the number of trainable parameters we have there. So from layer to layer. So we have to estimate the total number of trainable parameters. So we have 109,386 trainable parameters in that neural network like that. 1,009,386. So then we say the neural network contains neural network contains 109,386 trainable parameters. So, I mean, to interpret that, right, more trainable parameters generally increase the learning capacity of a neural network because it can model more complex relationships. So, however, larger models also require more training data, more computational resources, and stronger regularization techniques to reduce the risk of overfitting. So, it all depends. We have to find a balance between the accuracy of our model and the resources required to get that level of accuracy. So having done that, I can go back and show this again. So we have, don't forget the problems we're solving, the practice problems. Here you have one to five. You can see all of that. And then you have, okay, 1 to 5 again. Then six. I did six where we computed softmax probabilities. So you can see 6 to 15 here. You can see 6 to 15. And then we estimate the total number of trainable parameters. That's number 16. So here now we know for the weights between between input and first hidden layer. So the weights will be 784 times 128. Then the biases will be 128. So the total will be 784 times 128 plus 128. That's one side. Then next you have for the between the first hidden layer and the second hidden layer, the weights will be 128 by 64. 128 multiplied by 64 plus 64, that's the biases. And then between the second hidden layer and the output, you have the weight 64 times 10, then plus 10 for the biases. So that's the way that goes. So let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, why not go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can become a member of the channel by clicking on join. Just go to my channel and click on join. You'll find some special packages for you, some special benefits as a member of the channel. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.